So today we will continue with some mutual inductance examples, and let's start with the first example. Right. So in this example, I'm going to give you two coils, two inductances. Right. I'm going to give you their inductance in the frequency domain, because I'm going to assume that all the signals that you're going to apply, the inputs, the sources that are going to apply, are going to be sinusoidal. So I'm going to give you the self-inductance as j omega L1 and j omega L2, but furthermore, there is going to be some coupling between them. So those two windings are coupled with M, certain mutual inductance. The way how this would might physically look, is you could find some magnetic material, some magnetic core, let's say, something like this. Well, let me draw it properly. So this is the core. So this would be like some magnetic material that is very good at bunching together and condensing magnetic fields, magnetic fluxes. And then you would have coil 1 and coil 2, right? And this is one way of forcing two coils to be mutually have a mutual term between them, right? So because now we have the self terms for each of the coils, but because the fluxes are shared between the coils, we have a mutual term between them. Right? If you had two coils just in the air, far apart from each other, typically there is still some M between them, but because the coils are so far apart and the field is condensed inside the coil, so the magnetic field is typically condensed inside the coil, it could spread out of the coil and fringe. So it's spread out of the coil is called fringing. So it could spread out and it could still reach the other coil, but the distances are far enough such that M will be very small. It will approach zero, right? It will still be there, but it will be minuscule. So for most practical circuits, you really don't get mutual inductance, a sizable mutual inductance, unless you design it that way. Okay? So this is how those two coils might look like. Okay? But as I said again, we don't really care about the physical configuration here. We are doing circuits. So the question is, what happens if I connect those two coils in different ways? How will that change the equivalent inductance of those coils? So let me show you what I mean. Let's study a bunch of cases. So let's take case 1. Case 1 is going to be just a series connection of the coils. So I have coil 1, right, j omega L1, and then the dot is here, and then I have coil 2, j omega L2, and again the dot is here. Right, so this is a configuration, right? I can connect the two coils like that. I want to find the equivalent inductance. Right? How do I find the equivalent inductance? Well, I could apply a test voltage, call it V arrow, a phasor. This is all in the frequency domain. And I could connect a test voltage and measure what the test current is, right? And then Z is just V over I, right? And then when I find this expression, I need to see what is the equivalent L that will give me the same Z. That's the best way of approaching it. In fact, that's the only way of approaching it, right? So what we can do now is we can apply, right? So you could think, hey, let me just divide by j omega L1 plus j omega L2. That would work if there is no mutual coupling between them. The existence of the mutual coupling complicates things a bit. We cannot just add the impedances, divide by the voltage to get the current. So, but what we can do though is KVL. KVL always applies. So let's go through the loop. So going through the loop using KVL, I end up with minus V, right? I'm going this way, clockwise, and then the KVL voltages are this voltage, drop, and this voltage drop. Both of those voltage drops. Right? So I want to calculate the first voltage drop. Again, like I said, this is there is a mutual term here. So the voltage drop here, we're going to have a self term and a mutual term. The self term is easy. The self term is just the j omega L1 times I. Right? Now comes the mutual term. The mutual term is going to depend on the current going into coil 2. But those two coils are in series, right? So the current is going to be the same. So there is going to be a j omega M I. Right? The question now is about the sign. What should the sign be here? Well, let's check. I is going into the dot. So that gives me the first positive sign. But that's not enough. I have to check the orientation of my voltage with respect to the dot on the first coil. The orientation of the voltage matches the dot, so this remains positive, right? And then I continue to coil 2. And again, I put in the self term, j omega L2 I, and then I need to put in the mutual term. Well, let me not commit to positive or negative yet. So let me say, j omega M, and the current in coil 1 is I, it's the same current. Now I need to determine, will this be positive or negative? Well, let's check. I is going into the dot, so it remains positive for now. Let's check the polarity here on the primary coil. Does it match the dot? Yeah, so this remains positive. So this equals 0. So I end up with this expression. Let me take V to the other side. I end up with V being, let me take I out, j omega L1 plus j omega L2 plus 2j omega M, right? I. Right? I can rewrite this as I take the j omega out, I end up with j omega L1 plus L2 plus 2M I. Right. So let's assume instead of this whole thing, there's an equivalent inductance here. What would the impedance be? The impedance would be j omega L equivalent I. So for this configuration, to give me the same voltage drop as the equivalent impedance inductance should equal this, right? Those two should equal each other should equal to each other to get the same voltage drop and the same current, right? So the L equivalent from just comparing the expressions is going to be L1 plus L2 plus 2M. So here's the interesting part. The inductance, when you connect it to those two in series, the inductance is not just the sum of L1 and L2. It's also has an extra term which is double the mutual inductance. So the mutual inductance increases the equivalent inductance. Right? It's not always the case though. Sometimes it could subtract it, reduce it, and we will see that when we study case 2. Okay. Case 2 is the same thing. Those two windings connected in series, only now the dots are opposite of each other, right? And then I have j omega L1, j omega L2, and this is M. So I take one of the coils and I flip it and I connect it this way. And same deal, I have to calculate the current that occurs when I apply a test voltage and use that to calculate the equivalent inductance. Let me do KVL. Right, so I start for the voltage source, I have minus V. Let me take it to the other side right away. Minus V becomes V. And then I hit this voltage and I hit this voltage as I'm going through the loop. Right, so let's start with the first one. The first one will have a self component, which is going to be j omega L1 I, and then the mutual component, which is J omega M. The current in coil 2 is the same as the current in coil 1. It's going to be I. Now I want to determine the sign. What would the sign be here? Well, let's check. I is leaving the dot, right, in the secondary coil. So that tells me that this is going to be negative, right? But I'm not done yet. On the primary coil, I need to check the polarity of the voltage with respect to the polarity of the dot. The polarity matches, so this remains negative. So I'm done with the first coil. The second coil, it has a self term plus J omega L2 I, and then it has a mutual term. So it has a J omega M, and current through coil 1 is going to be I. It's the same current. Now I need to determine the sign. I is going into the dot, so this is positive, right? But I'm not done yet. I need to check the polarity of the voltage I'm adding into the KVL equation with respect to the dot. Aha, notice here the polarity is opposite. The voltage polarity is this, but the dot is in an opposite configuration, so this becomes minus also. So I sum things up, I end up with V equals, I take J omega and I out, so I end up with J omega L1 plus L2 minus 2M I. Right, so this is equivalent to J omega L equivalent I, so L equivalent is L1 plus L2 minus 2M. The mutual inductance reduces the total equivalent inductance. Okay. So that's case 2. What are the other cases? Well, I mean, we examined connecting the coils in series. The other 2 cases have to do with connecting the coils in parallel. If I take those 2 coils and connect them in parallel this way, with the dot aligning, L1 J omega L2, and there's M J omega M in between. Yeah, the question now is what is the equivalent inductance here? So here I have 2 currents, I1 and I2, and then total current I, and then a test voltage that I apply. Right? So this involves the current branching into 2 parallel branches. So we need to kind of write the equations for this. What is, let's start with the first branch. For the first branch, this is the voltage, right? So it's going to be V. This voltage is going to be equal to the voltage across the coil, right? This voltage. What is the voltage across the coil? The voltage across the coil has a self term and a mutual term, again, as usual, with mutual inductance. So the self term is going to be J omega L1 I1. What about the mutual term? The mutual term is going to be J omega M, and it's going to be dependent on I2, right? It's going to be dependent on the current in coil 2. That's why it's mutual inductance. It's the current in I2 in coil 2 affecting coil 1. Now we need to determine the side, the sign, right? So let's start with the dot convention. I2 is entering the dot, so that's positive. But we're not done. Is the polarity of the voltage I'm interested in the same as the polarity of the dot? Yeah, so this remains positive. And then I go to the second branch. V, again, equals the self term, J omega L2 I2, and then I have the mutual term J omega M I1. Now the question is the polarity, the sign. Is I1 entering into the dot? Yeah, that's positive. Is the polarity of the voltage here I'm interested in the same as the dot? Yeah, so this remains positive. So I have 2 equations with 2 unknowns, I1 and I2. I can solve this, of course. I can write it as a matrix equation. So I have I1 and I2. This equals V, and then the terms here are Well, I1 here is multiplied by j omega L1, j omega m, that's what multiplies I2, and then I have j omega m, and then j omega L2. What I can do here is I can take j omega out, and then send it to the other side, so this becomes 1 over j omega v v, and this is I1 I2, and this is the matrix L1 M M L2. All I need to do now is invert this matrix, so, and I get I1 I2. Right, I1 I2 is just going to be 1 over j omega, this matrix inverted, v v. We know how to invert a matrix, right, from linear algebra. At least we know how to invert simple 2 by 2 matrices, right? So this is going to be first, it's going to have the inverse of the determinant. So I need to take the determinant of this matrix and invert it. That's the first step. So that's going to be, what's the determinant? L1 L2 minus m squared, L1 L2 minus m squared. That's the determinant of this matrix. And then I have now to take the transpose of the cofactors. So I need to fill in this. What's this thing going to be? This thing is going to be the cofactor of L1. The cofactor of L1 is L2, right? So this is going to be L2, right? And then I move to m, because I move from this is going to be positive minus, positive minus. I move to m, the sign is going to flip to negative, right? I need to find the cofactor of m, and because this is transpose, I'll fill this is what the cofactor of m will go here. So the cofactor of m is going to be this. So I take this out, this is out, this out. This is a cofactor of m. So this is going to be m, right? But then because this has a minus sign, this becomes minus m, right? And then I find the cofactor of m. It's going to be m again. So this is, but this is has a minus sign, so it's going to be minus m. Right, the cofactor of L2 is going to be, the sign is going to be positive again, because we go positive, minus, and then positive as we permute on the matrix. Please review this, at least for 2 by 2 matrices. You should know how to do this. Right, the cofactor of L2 is going to be L1. So this is L1. So this is the inverse for this matrix. And you can check. You can take this matrix and multiply it by this matrix, and you should get unity, the identity matrix. And this is it. This gives me the solution. So this gives me I1 equals, so it's going to be V1 times L2 minus V times L2 minus V times M. So it's going to be V L2 minus M divided by this term, divided by j omega L1 L2 minus M squared. And then I2 is going to be V times now L1 minus M. So I'm going to have L1. I'm just doing the matrix multiplication. That's all. Divided by that same constant, L1 L2 minus M squared. Okay, what's the total current going into the circuit? The total current going into the circuit is just I1 plus I2. So all I need to do is sum those two terms up. I end up with V. I take V out as common factor, and then I have L2 minus M plus L1 minus M. So this becomes L1 plus L2 minus 2M, right, over j omega L1 L2 minus M squared. Right. So this should equal to V. I should equal to V over j omega L equivalent. Right, I can compare those two expressions, and I clearly see that L equivalent is going to be L1 L2 minus M squared over L1 plus L2 minus 2M. Minus or Yeah, minus. Okay, so this is L equivalent. Of course, what's case number 4? Case number 4 is the same, only now the dots are inverted like this. Right, so we don't even need to solve this, right? Why don't we need to solve this? Because right, we don't need to solve this because this just requires us to make m negative. Right, this is going to be the same thing. Let me show you why. So let's write the equations actually for case 4. So v equals, so this is I1 and this is I2 and this is I. So v equals j omega, this is j omega L1, j omega L2 equals j omega L1 I1, right? And now I have the mutual terms j omega m. It's good to do it just to show you what happens, right? J omega m I2, right? But now I want to determine the sign. So first here I2 is going out of the dot, so the sign is negative. And the polarity I'm investigating here on the primary coil is the same polarity as the dot, so this remains negative. V now is also equal to j omega L2 I2, the self term, and then I have the j omega m I1, the mutual inductance term. What about the sign? Well, I1, so this is the voltage I'm interested in. So this is also interesting to look into. I1 is going into the dot, so it's just, this would indicate that this would be positive, but that's not enough. We have to look at the polarity of the voltage I'm interested in versus the polarity of the dot. The polarity of the dot is inverted with respect to the voltage I'm interested in, so this becomes negative. So we end up with the kind of like the same kind of matrix. We end up with j omega L1 minus m L2 I1 I2 equals V1 V2. This is exactly the same matrix we got the last time. The only difference is that instead of m we have minus m here. So to find the solution here, all we have to do is that instead of m we plug in minus m in this expression. The m squared will be the same, right? Because m or minus m squared is going to give me the same value, but this will change. So L equivalent in this case is going to be L1 L2 minus m squared over L1 plus L2, and then instead of minus 2m, I end up with plus 2m. I think I might have made a mistake somewhere here. I think no. Yeah, I think I inverted something wrong here. Did I? No, this is probably right. I'll double check, and if there's a mistake, I'll correct it. But I think this is right. Okay. If it's wrong, there is just a flip in sign somewhere. But the important thing is that L equivalent is this, and to find the L equivalent for the other case, just flip the sign of M. All right. Okay, I double checked. The calculation is correct. The confusion was due to my notes. I flipped a sign somewhere in my notes. Okay. So let's do the other example now. Okay, so the example is this circuit. And this is an example where we kind of touch upon the concept of a transformer. This is an example of using coupling to connect from one circuit to the other circuit. So we have one circuit and then we have another circuit. and then we use coupling to connect between those two circuits so that energy is transferred one circuit to the other. So this is coupling, and the coupling here is, I'm going to just give it to you numerically, it's going to be G2 ohms. So 2 ohms is equivalent to omega m. Right. This here is an example of a transformer, and we're going to study transformers in a little bit more detail, particularly the ideal transformer. But this is like the first example of a transformer. Right? The goal is now to find VO here on the secondary circuit due to the input voltage here, which is 2430 degrees volt. And I'm not giving you RMS here, so you don't need to assume that it's RMS. You don't need to assume that's RMS. It's not RMS. Right, so this here coil is J omega L1. I'm going to give it to you numerically right away. This is J4, and J omega L2 is just going to be J6. So those are the self impedances, and this is the mutual impedance. And the capacitor, of course, is going to be minus J2 ohms, and this resistor is 2 ohms. So yeah, we want to solve this. The easiest way to approach this is just to do mesh analysis to solve for I1 and I2. Okay, so let's write the mesh equations. Let's start with mesh number 1. So we have minus 24, 30 degrees. And then we have plus 2 I1. And then we have plus J4 I1. This is the self term. The mutual term is going to be J2 I2, of course. And I want to determine the sign. I2 is exiting the dot, so this is going to be negative, and then the polarity of KVL I'm doing here matches the polarity of the dot on the primary side, so this will remain negative. This will be 0. So I have equation number 1 already. So let me collect the terms. I have 2 plus J4 I1 minus 2J I2 equals 2430 degrees. This is equation number 1. And now I want to write equation number 2. So let me go through the second loop. Through the second loop, I have J6 I2. This is the self term. Right, simple enough. And then I want to put in the mutual term. The mutual term is so J omega m is going to be J2 ohms times I1. Now what's the sign here? Well, I1 is entering the dot, right? So this would suggest that there's no sign flip at the beginning. So this would suggest that this could be positive, but we have to continue now. So I1 is entering the dot, so there's no sign flip. But then, because I'm doing KVL in this direction, clockwise, the KVL voltage has a polarity that's opposite to the dot. So this becomes minus. That's why the minus comes in, because the KVL voltage has a polarity opposite to the dot as I'm traversing the loop. Right? And I'm done. I'm gonna continue. This is the mutual term, and then I'm gonna continue with the capacitor and the resistor. So you have minus J2 I2 plus 2 I2 equals 0. And I'm ready to collect terms to get equation number 2. So I'm gonna have minus J2 I1, and then I have 3 I2 terms. I'll have this term, a real part, and then imaginary part. So I have plus 2, this is the real part. Imaginary part is J6 minus J2, which is J4. So it's going to be plus J4 I2 equals 0. This is equation number 2. 2 equations, 2 unknowns. I can solve this, right? So I'm going to have 2 plus J4 minus J2. This is from equation 1. I1, I2 going to equal 2430 degrees. and then minus J2, 2 plus J4, 0. And all I need to do is solve this, invert this matrix and take it to the other side and solve this. I just went to MATLAB to solve this. I mean, you don't need to solve this by hand. So I2 is going to be 2.6. When you do all the number crunching, I2 turns out to be 2.68, 3.43 amps. Right? And then readily you can solve for VO. VO is just 2 ohms times I2, right? That's what it is. So VO is going to be 5.37, 3.43 degrees. That's this example. Let's do like a bigger example with mesh analysis. So this is another example. So we have the voltage. So guys, typically, I mean, I like to do the examples in the textbook. I mean, the authors put a lot of thought on what representative examples to put in. But if you guys encounter any problem that you would like me to solve as an example, I mean, feel free to recommend that too. That might allows us to run into some interesting ideas that we might discuss if there is a difficulty in that example you encounter. Sometimes examples will be trivial, right? But the examples in this textbook are good. I like them actually. Some of the best examples I've seen in any textbook. All right, so let's do this. So I have an inductance. I won't draw the dots yet. Capacitor, R2, another inductor. I'm going to leave everything symbolic. R4, R3, R1, R2, R3, R4, 4 resistors, 2 capacitors. The impedances of the capacitors are 1 over j omega C1 and 1 over j omega C2. Right? And then I have j omega L1 and j omega L2. Regular 3-mesh circuit. The twist here now is that there is a mutual inductance between those two inductors, which is j omega M. And the dots are this way. All right. So the problem is to write the 3-mesh equations: I1, I2, I3. Okay. So I want to do this problem a little bit differently. I mean, you could easily write the 3 equations. I want to show you that you can easily populate the matrix right away without having to I need to show my circuit, right? But you can easily populate the matrix right away without having to write the equations. Perhaps in some problems this is simpler, in some problems it's not. So I have I1, I2, I3. There are 2 things we need to populate. We need to populate this matrix, and then we need to populate the output vector here. Okay? And we can do this by examination. So let me start with the first loop. The first loop, I'm going counterclockwise, so I hit minus V. But then I can take minus V to the other side, so I end up with V here. So this is the term that I'm plugged in right away from the first equation. Here I have I1 times R1, so I can put in R1 here in the first spot. Right? Then I have I1 minus I2 times this term here. So I have this inductance. So let me start with the self-inductance. So I have I1 minus I2 times the self-inductance. This, I can populate this right away. Since this I1 is positive and I2 has the negative sign, I can populate this right away by plugging in plus j omega L1 here in this first, right? Because the first element is the factor of I1. The second element is the factor of I2. And then I'm going to put in minus j omega L1 in the second element of the matrix. Right? And I'm done as far as the self-inductance is concerned. Now I need to plug in the mutual inductance. Okay, the mutual inductance is interesting. The mutual inductance is going to be j omega m, right? It's coming from I2 minus I3, right? So I2 minus I3 goes into this dot times j omega m, gives me the mutual voltage that appears in coil 1, right? What is the polarity? Well, I'm examining KVL, right? KVL, I'm examining it this way, so the polarity of the voltage is the same as the polarity of the dot. And by design, I made sure that the current goes into the dot because I took I2 minus I3, right? So the polarity should be positive, right? And now this is easy. This is here plus j omega m, right? Minus j omega m. The minus sign comes from this minus I3. Okay, so I already populated this, and then I have the last element, which is the capacitor, which is going to be 1 over j omega c, right? So it's going to be plus 1 over j omega c1, but there's an I1 minus I2 here going into the capacitor, so I have minus 1 over j omega c1 in the I2 slot, and I already populated all three elements of the first row instantly without writing the equations. Right. Now let's jump to the second row. In the second row, notice there are no, the second row has to do with the second mesh. Notice there are no voltage sources or current sources. Well, this is KVL, so there's no voltage sources, so this will be 0. And now I want to start populating the second row. So let me start with all the self and impedances, and then worry about the mutual impedance. So if I start with all the self impedances, I start with 1 over j omega c. The current going through it is I2. As I go through the loop, the current going through it this way is I2 minus I1, right? So it's going to be 1 over j omega c1 minus 1 over j omega c1, I2 and I1, right? And then I have the mutual, the self-inductance, which is j omega L. Again, it's going to be I2 minus I1, so it's going to be plus j omega L1 minus j omega L1, right? And then I have R2. R2 is just multiplied by I2, so this is going to be plus R2. I'm going to write it up there. And then I have, going in this direction, I have I2 minus I3 j omega L2. So it's going to be plus j omega L2 minus j omega L2 because of the minus I3. And then I have I2 minus I3 times R3. So it's going to be plus R3 minus R3. Okay, and I'm done with all the elements except now the mutual terms. So there's a mutual voltage here that I haven't accounted for. There's a mutual voltage here that I haven't accounted for. So the mutual voltage here is what? Here is what? It's going to be j omega m, right, times the current passing through the dot, which is I2 minus I3, right, and then the right, so that's it, j omega m, I2 minus I3. But then by design I2 minus I3 goes into the dot, but then the KVL voltage I'm interested in is opposite to the dot because I'm going clockwise, so this needs to be negative. Yeah, think about that. So this has to be negative, right? So there is a minus j omega m in I2. So there is going to be minus j omega m in I2, and there's going to be its inverse in I3, so it's going to be plus j omega m. Okay, and then we have to find the mutual voltage in the second coil. Here in this coil, by design, I take I1 minus I2 to go into the dot, right? And this is times j omega m. That's the mutual voltage appearing in this coil, right? But again, the voltage, KVL voltage, is going to be this as I go through the loop, and this matches the polarity of the dot, right? This plus minus matches the polarity of the dot as I'm going KVL, and the current by design here is going into the dot. It's I1 minus I2, so this is positive, right? So there's going to be plus j omega m here in I1, and minus another minus j omega m in I2. This is going to be minus minus j 2 omega. There's another minus j omega m that happens there. Okay, and I'm done. I populated the 3 elements of the second row by inspection. Now I need to move to the third row. Let me expand this, and I want to populate the 3 elements by inspection. Okay, so the third row has to do with this loop. Let's start with all the self terms. So I have R3 times I3 minus I2. So I'm going to have R3 minus R3, and then j omega L2 here plus j omega L2 minus j omega L2. Again, you flip the sign when you go between I3 and I2, right? And then only in I3 I'm going to have 1 over j omega C2, so I'm going to have 1 plus 1 over j omega C2. And then finally, only in the third mesh, I'm going to have R4. So I'm going to have plus R4. So that takes care of the mutual terms, of the self terms. Now I want to take care of the mutual term. Okay. So there's a mutual voltage here. And this mutual voltage is what? It's j omega m I1 minus I2. All right, but what about the sign? Well, I1 minus I2 goes into the dot, right? But when I'm going clockwise here, the voltage of the KVL voltage that I'm interested in is opposite the sign of the, is opposite of the dot, opposite of the polarity of the dot. So this becomes minus here. So there's a minus j omega m I1. So there's a minus j omega m in the I1 column. And then there's a plus j omega m in the I2 column. So there's a plus j omega m. And that takes care of the mutual terms. And I'm done. I completely populated this matrix. Okay. This is 0, by the way. There is no sources in the third mesh. And there are no sources in the third mesh. Okay. Let's do another example. So let's do an example that tells you how to do, like, shows you how to do an equivalent impedance. Okay. Say you have this circuit. We did equivalent inductance, but we did not do equivalent impedance. Say we have this impedance ZL, ZS, Z source. S means source, source impedance, and then we have this transformer, which is just a set of mutually coupled inductors. Right, I have j omega L1, j omega L2, I have j omega m mutual impedance between them, and then I have a load impedance. So the question is, what is the equivalent impedance looking into the circuit? Right, we've already equipped with tools to solve for this, right? Solve this problem. So I just have to do the two meshes, I1 and I2. And let me do the mesh analysis. So I go minus Vs, I put it to the other side instantly. So this is going to be Vs equals, I put in the self terms, just Js plus J omega L1 I1, right? And then I now have to put in the mutual term, the mutual voltage that appears here. So this is going to be J omega M. It's going to depend on I2, of course. And now I need to determine the sign. I2 is leaving the dot, so this is minus. And the KVL voltage I'm interested in is the same polarity as the dot, so this remains minus. Okay, loop number 2, 0 equals. So so let's start with the mutual term, right? Just the mutual term is a function of I1, right? So it's going to be J omega M I1, right? That's what it is. It's going to be I1 imposing itself on the coil 2. And what about the sign? Well, I1 is going into the dot, so this suggests that the sign could be positive. But then I have to examine the polarity of the voltage I'm interested in. I'm doing KVL clockwise, so the polarity of the KVL voltage is this. So I'm going in this direction. Right, the polarity is opposite the polarity of the dot, so this actually needs to be negative. And now the rest is just the self-impedances. So this is going to be ZL plus J omega L2 I2. Right? Because here we have 0, we can easily solve for I2. I2 is going to be J omega M over ZL plus J omega L2 I1. And then we can plug in this I2 here. So we end up with Vs equals Zs plus J omega L1 I1. So J times minus J is 1. Omega times omega is omega squared. M times M is M squared. Over ZL plus J omega L2 I1. I can divide both sides by I1. So I end up with Vs over I1, which is equal to Z equivalent. This turns out to be Zs plus J omega L1 plus omega squared M squared over ZL plus J omega L2. And that's it. This is the equivalent impedance. Notice the curious thing is that M is squared. Because M is squared, that means that the impedance does not depend on the polarity of the dots in this case. Because why? Because it shows up as M squared in the equivalent impedance equation. Yeah, so that's an interesting configuration. And it makes sense that it doesn't depend on the dot, because really, I mean, impedance is symmetric. If I take an impedance and I flip it, I'll get the same thing. So it really doesn't matter, whatever current is coming here, it doesn't matter how you feed it into the impedance, whether you feed it this way or feed it in the opposite way, the impedance will look the same. That's why the equivalent, that's the deep reason why the equivalent impedance does not depend on the dot orientation. All right. So I guess we are done with examples, and I want to move on to the next section if we have time. I think we have some time. Let's see. Okay, I think I'll end this lecture here, because the next section, I guess I prefer to start it with a fresh lecture. All right. Thank you guys. See you next time.